So I just gave an exam in my differential equations class, and well, I thought I'd make a video going through the solutions, mostly for my students, but I thought that maybe it would have a broader interest. So let's do it. The first question is to verify that the function y equals the integral from 1 to x of sine of t over t squared is a solution to the following differential equation. We have x cubed y double prime plus 2x squared y prime equals x cosine x. And now this is really just an exercise in finding derivatives, and especially using the fundamental theorem of calculus. Okay, so let's start by finding the first and the second derivative of our function y. So by the first fundamental theorem of calculus, or the second, depending on which book you're looking at, y prime is going to be equal to sine of x over x squared. Now, I'm not really going to review why that's the case, but it is, and it's something to keep in mind if you're in a differential equations class that you might need something like this from your calculus classes. Okay, so now that we have this, let's find the second derivative. And I'm going to find the second derivative by looking at this as sine of x times 1 over x squared using the product rule. So the derivative of sine of x is cosine of x. That's going to give us cosine of x over x squared. The derivative of 1 over x squared is negative 2 over x cubed. That'll give us minus 2 times sine of x over x cubed. Could you use the quotient rule here? Well, of course you could, but I think it's simpler to do it this way. So now let's do x cubed times y double prime plus 2x squared times y prime, and ensure that we get x times cosine x. Let's observe that this x cubed will cancel out these denominators in my y double prime and leave me with x times cosine of x minus 2 times sine of x. Because we just have an x squared in the denominator of cosine, so when we multiply by x cubed, it cancels as such. Okay, now multiplying by 2x squared will cancel the x squared in the denominator of sine x over x squared, leaving us simply, let's see, 2 times sine x. So we have plus 2 times sine of x. But now let's observe that the 2 sine x and the 2 sine x cancel, leaving us with x cosine x, which is where we wanted to end up. Okay, so for question 2a, we need to solve the differential equation y prime times cosine of y equals sine x times sine y. This is a separable differential equation. Let's maybe take this y prime and write it as dy by dx, and then we'll abuse notation to move all the x's to one side, all the y's to another side, including the dy over dx. So let's see, that's going to leave us with something like cosine of y over sine of y dy equals, let's see, sine of x dx. Now we'll take the antiderivative of both sides with respect to y on the left and x on the right. Let's observe on the left, we might want to do a quick u substitution. U equals sine of x. That makes du equal to, that should be sine of y, cos y dy. That means that's going to integrate to the natural log of u, or the natural log of the sine of y here. And I'm not going to put absolute values here. Of course, to be really careful, you would, but let's just assume that we're in a domain where sine is positive for the sake of argument. Okay, so we've got natural log of sine of y equals, so the antiderivative of sine x is negative cosine of x. So we have negative cosine of x, and then it's going to be plus a constant, but I'll write it as a constant minus cosine of x, just to keep it looking a little bit tidier. And now that's going to be an implicit solution. Could you solve for y? Well, yeah, you could, but it'd be a little bit gnarly, and it's not strictly necessary for this problem. But I'd do one more step. Maybe sine of y is equal to some constant times e to the minus cosine of x, where I've kind of absorbed or renamed the constant in the exponentiating process. Then we could take the inverse sine of both sides if we wanted to, and we'd be good to go. Okay, so now let's look at this next one. We have 2x minus 1 times y minus 1 plus x plus 2 times y plus 3 times y prime equals 0. This is another separable differential equation. Observe that we can write it as, let's see, y plus 3 over 1 minus y times dy equals, let's make sure to get this right, 2x minus 1 over x plus 2 dx. So again, that's just from moving some stuff around. We're not going to go into exactly how we solved down to that point. I think that's pretty straightforward. And now we can look at each of these, keeping in mind that we need to find the antiderivatives. And we've got a polynomial on the top and the bottom that have the same degree, which tells us that we should be doing some sort of division. So in fact, you can take this first term, the y term, and rewrite it in the following way. Let's make sure to get this right. It's going to be minus 1, and then it'll be plus 1 over 1 minus y dy. And now if you need to see why that's the case, you could give this a bit of a common denominator real quick. Let's observe that this minus 1 can be written as y minus 1 over 1 minus y. And then, oh, that should be plus 4 then. So notice when you add those back up, you end up with the y plus 3 over 1 minus y. That's why that works. Now we're going to do something similar over here. So we'll have 2, and then it'll be minus 5 over x plus 2. But now that's the same thing as we did over here. We're just noticing that if you were to combine those back together, you would get what we have above. But now we can take the antiderivative of both sides pretty easily. This gives us minus y minus 4 times the natural log of, here I'll put the absolute values in here, absolute value of 1 minus y. And then over there on the right-hand side, we're going to have 2x, and then it'll be minus 5 times the natural log of the absolute value of x plus 2 plus a constant. And, well, this is again one that, in this case, you really have to leave it in implicit notation. It's pretty much impossible without using a special function, I should say, I think the Lambert W function, to solve for y. So we would take that as our solution. Okay, let's move on to the next set of problems. Okay, so the third problem, which isn't written on the board, was a short answer question, if you will, of why we need a numerical way to approximate solutions to differential equations. And the reasoning was many interesting differential equations that you find modeling natural phenomenon in fact don't have analytic solutions, and so the only way to study what their solutions look like is using numerical methods. Okay, and then that jumps right into a test over Euler's method. So let's say we're given the differential equation y prime equals t squared plus y cubed, where y of 0 equals 1. Our goal is to approximate y of 1 with Euler's method and a step size of 1/2. So that means we're going to need 2 steps, because it takes 2 steps of step length 1/2 to get to the point 1 along the t-axis in this case. I think that goes without saying. Okay, so let's observe that generally we have x0 plus h times k is the formula for the kth iterate of x. And so that is true for everything set up with Euler's method. But notice in our case, x0, if you will, is just equal to 0. So that means our xk is simply 1/2 times k, or it's k over 2 because we're having a step size of 1/2. So that means we've got x sub 0 is 0, x sub 1 is 1/2, x sub 2 is 2/2 or 1, x sub 3 will be 1.5 or 3/2, and so on and so forth. We only need 2 steps, so we're not going to use anything past x2, but just keep that in mind. We actually won't use x2 because that'll be our ending point, but that's kind of neither here nor there. And then also, let's just recall the general formula for Euler's method, which is y sub k plus 1 equals y sub k plus h times f evaluated at xk, yk, where this is, in the case that we have a differential equation, y equals, let's see, f of x comma y. And I guess I'm like being a little loose with my x's and t's here. And so just to remedy that, let's change this t to an x. So I don't have to change the rest of these x's to t's, just the same kind of thing. And then let's observe here that y sub k is meant to approximate y evaluated at x sub k. Okay, so again, like that's all the review of Euler's method, and now let's jump right into it. So for us, y sub 1 is going to be equal to y sub 0 plus our step size, which is 1/2, times our function. Notice our function here is simply this x squared plus y cubed evaluated at x0, y0. So that's going to be 0 squared plus 1 cubed. Okay, and then I guess y0, let's insert that in there. That's simply 1. Okay, so that's everything inserted into Euler's formula for y sub 1. So let's see, we're going to have 1 plus 1/2, we're going to have 3/2. And now let's just note that that means that y evaluated at 1/2 is approximately equal to 3/2. Okay, great. Now let's do the next step. So we have y sub 2, so that's going to be y sub 1 plus 1/2, and then x1 squared plus y1 cubed. Again, that's our formula. So y sub 1 is 3/2, we just calculated that, plus 1/2. And then x sub 1 is 1/2. So x sub 1 squared is 1/4 plus y sub 1 was 3/2. So if we cube it, we get 27/8. So that's our y sub 2. Now you can add that up if you want to. Actually, maybe let's do that. So that's going to be 3/2 plus 1/8 plus 27/16. We got to give that a common denominator. That's going to be a 2/16. Multiply that by 8. That's going to be a 24/16. So let's see. We have 24 plus 27. That's going to give us 51 plus 2 is 53/16 is the approximate value of y of 1. Okay, so there, we've approximated y of 1 there. Okay, so now let's move on to this next one. Our goal here is to take the following non-exact differential equation. We have 2x squared y plus y to the 4th plus x cubed times plus xy cubed times y prime equals 0. So you can check that's non-exact, but it was given on the exam that it's non-exact. But it was also given on the exam that you can make it exact with an integrating factor of the form x to the alpha times y to the beta. So let's multiply by that integrating factor and see what it takes to get an exact differential equation. So we'll have 2 times x to the alpha plus 2 times y to the beta plus 1 plus x to the alpha times y to the beta plus 4. We're just multiplying through here, nothing fancy. X to the alpha plus 3, y to the beta, and then plus, let's see, x to the alpha plus 1, y to the beta plus 3 times y prime equals 0. So in order for this to be exact, we need to be able to take the partial with respect to y of this function and it be equal to the partial with respect to x of this function. That's the exactness condition. Okay, so let's see what it would take for that to occur. So taking the partial with respect to y of this will give us 2 times beta plus 1 times x to the alpha plus 2 y to the beta plus, let's see, beta plus 4 times x to the alpha y to the beta plus 3. And like I said, we need that to be equal to, in this case, alpha plus 3 times x to the alpha plus 2 y to the beta plus alpha plus 1 times x to the alpha y to the beta plus 3. And then, well, we've got two types of powers of x and y on both sides of the equation. That means we can set them equal to each other. So we've got this bit right here, which is the x to the alpha plus 2 y to the beta term. That has to be equal to this bit. And then the same thing, this bit, the other term, x to the alpha y to the beta plus 3, has to be equal to this bit. In particular, their coefficients have to be equal. So let's see, that's going to give us 2 beta plus 2 equals alpha plus 3. That's from the yellow underline. And then we're going to have beta plus 4 is equal to alpha plus 1. Okay, nice. But now let's observe that we can take these two equations and subtract them. And we'll have 2 beta minus beta, which is beta. 2 minus 4 is negative 2 equals alpha minus alpha is 0. 3 minus 1 is 2. So beta minus 2 is 2. In other words, beta is equal to 4. And then we can plug that back here. We have alpha plus 1 equals 4 plus 4. So alpha plus 1 is 8. Alpha is equal to 7. So there, we've got alpha equal to 7. Now we can plug those into our equation right here, and we know that that new thing is exact by construction. So let's see, now our differential equation is 2 times x to the 9, and then y to the 5, plus x to the 7, y to the 8, and then plus, let's see, that's going to be x to the 10, y to the 4, plus x to the 8, y to the 7, y prime equals 0. Okay, and then since we've got an exact differential equation, we're guaranteed to have a function x and y. So there exists a function x and y where this first thing is equal to the partial of f with respect to x, and this second thing is equal to the partial of f with respect to y. That's from the solution strategy for exact differential equations. So if the partial of f with respect to x is this, then we can take the antiderivative with respect to x of both sides, and we have f of xy equals, let's see, antiderivative with respect to x will give us 2 over 10, or 1 over 5, x to the 10, y to the 5th, plus, let's see, it's going to be 1 over 8, x to the 8, y to the 8. Okay, nice. And then, well, since we took an antiderivative with respect to x, that means we'll have potentially a function that's only a function of y. But now we have to check that against this f sub y thing. So we'll take the partial of this with respect to y and make sure everything works out. So if we take the partial of this with respect to y, observe, we get x to the 10, y to the 4 from the first term using the power rule. We get x to the 8, y to the 7 by the second term using the power rule, plus g prime of y. But let's observe that this term right here matches this term right here. So that means g prime is simply equal to 0. In other words, g is a constant. But that means that we don't have to fix our function at all, and we have our final solution, which is our function f equal to a constant. That's the implicit description of our final solution. So let's see, we've got this y to the 8 equals some constant. There we have it. Okay, now let's move on. Okay, so the next problem is a nice mixing problem. So let's say that water with 5 grams of pollution per liter is flowing into a 1,000 liter tank at a rate of 3 liters per minute. And that tank initially has 2 grams per liter of pollution dissolved in 500 liters of water. So the maximum volume of the tank is 1,000, but it starts off at 500. Then the solution mixes and drains at a rate of 1 liter per minute. Our goal is to find a function describing the amount of pollution in the tank. We're going to start with a word equation. So let's let P of t equal the amount of pollution in the tank at time t. Now notice that dp dt, or p prime if you will, is going to be the rate of the pollution flowing in minus the rate of the pollution flowing out. Those are the only two ways that this can change in this scenario. Now notice that the rate of the pollution flowing in is pretty straightforward. We get 5 grams per liter of pollution at 3 liters per minute, so we have 15 grams per minute coming in. Now the rate going out is a little bit trickier, but let's maybe outline how to figure that out over here. So notice that the rate of it going out is going to be equal to, let's see, the concentration of the tank times really what I'll just call the flow rate. And so notice that we know the flow rate immediately. The flow rate is 1. So then all we're going to really have is the concentration of the tank times 1. But the concentration of the tank is the amount of pollution in the tank, which we said was P of T, divided by the current volume of the water in the tank. But we can figure that out pretty easily. So this is going to be P over, notice that the current volume can be calculated by the fact that we start with 500 liters of water, and since 3 is coming in and 1 is going out every minute we gain 2 liters of water. So that means in the end, the current volume of water in the tank is 500 plus 2T. But now we can put that over here. We've got P over 500 plus 2T. Bring this P prime down, and we've got a first order linear differential equation. Now let's put it into the standard form for a first order linear differential equation. We have P prime plus 1 over 2T plus 500 times P equals 15. And so in class, we had a formula for this. So we found our alpha function first. So alpha of t is going to be the exponential of the antiderivative of the function that was in front of p here. And so that's going to be the antiderivative of 1 over 2t plus 500 dt. But that antiderivative is pretty straightforward. We're going to have the exponential of 1/2 times the log of 2t plus 500. Here we really don't need absolute values because that's always a positive function. You can't have a negative volume in the tank. But now we can take this half here, get rid of it, and put it up here as an exponent, and then the exponent and the logarithm can cancel, and we've got 2t plus 500 to the half power. I'm going to leave it like that, just because it'll keep it simpler for our final calculation. Okay, and then our p of t function is going to be 1 over alpha times some constant plus the integral of, let's see, this function right here, which is alpha, times this function right here, which is 15. So it's really just 15 alpha dt. Okay, but now let's get to this calculation. So that's going to be 2t plus 500 to the minus half times a constant, plus we have 15 times the integral of 2t plus 500 to the half. That's just using that formula we developed whenever we did first order linear differential equations. Now we can take the antiderivative of this bit pretty easily. Notice the antiderivative of this bit is going to be 1/3 times 2t plus 500 to the 3/2. We increase the exponent by 1. We divide by the new exponent. Dividing by 3/2 is the same thing as multiplying by 2/3, but we lost the 2 in the numerator because of this 2 right here in front of the t. Okay, so now let's start putting some things together. So we're going to have c over the square root of 2t plus 500. And then plus, we've got 15 over 3, that's going to give us 5. And then we've got this 2t plus 500 to the minus half times 2t plus 500 to the 3/2. So in the end, that's just going to give us 2t plus 500 to the 1, if you will. And then this is our p of t. But of course, we can find our c value here because, well, there's something we haven't used yet, and that is we've got an initial condition. Notice that there's initially 2 grams per liter of pollution in 500 liters of water. That means that we know P evaluated at 0 is equal to 1,000. So let's see, we've got P evaluated at 0 is going to be C over the square root of 500 plus, let's see, that'll be 2,500 equals 1,000. So now it's pretty straightforward here to solve for c. So I'll maybe leave it here. You can solve this for c and plug it into our function up here, and then, well, we've got a function describing the pollution in the tank at time t. Okay, so just a couple more. All right, we've got two more. So the first is to find the most general solution to the differential equation 6y double prime plus 5y prime minus 4y equals 0. So of course, here we're going to look at the associated polynomial, which is 6 times r squared plus 5 times r minus 4 equals 0, and look at its roots. So how does this thing factor? Well, you can play around with it a little bit, and you'll see that it factors as 3r plus 4 times 2r minus 1. So notice the cross terms here work out, if you will. We have 4 times 2 is 8, minus 3 times 1 is 5. So that gives us our middle term. But notice the roots of this are minus 4/3 and a half. But that means our general solution is c1 e to the minus 4/3 x plus c2 e to the half x. And that's really all there is to that. So the next one involves Abel's theorem. So let's say we know that y sub 1 equals x squared is the solution to the differential equation x squared y double prime minus 3xy prime plus 4y equals 0. Our goal is to find a second solution. Now, if you've gone a little bit further in a differential equation class, you know generally how to find all solutions for these types of differential equations. But in this class, at the moment of the exam, we did not know that method. Okay, so the trick here is to look at the Wronskian two different ways, one using the definition and one using Abel's theorem. So using the definition, the Wronskian is going to be equal to y1, y1 prime, and then y2, y2 prime. But I'm just going to write the y2 as y because that's going to be our unknown second solution. So we're building a differential equation for that. But notice that y1 is x squared by the given, y1 prime is 2x by taking the derivative. So that means our Wronskian here is x squared y prime minus 2x times y just by rules of the derivative. Now also, Abel's theorem tells us that the Wronskian here is the exponential of minus the antiderivative of the function that's in front of y prime, but not quite the function in front of y prime, the function in front of y prime after scaling the differential equation. So 1 is in front of y double prime. So that would be y double prime minus 3 over x times y prime plus 4 over x squared times y equals 0. So that means the function in front of y prime is this minus 3 over x. But again, like I said, there is a minus sign built into the formula in Abel's theorem, so it's going to cancel. And we're going to get the exponential of 3 times the antiderivative of 1 over x dx when all is said and done. But of course, that's going to be the exponential of 3 times the log of x, which is the exponential of the log of x cubed using exponent rules, which is x cubed. But now we can just set the extreme left and right side of this equation equal to each other. And that gives us a first order differential equation, a first order linear differential equation, that is. So we have x squared y prime minus 2xy equals x cubed. Now we'll divide all parts of this equation by x squared. That gives us y prime minus 2 over x times y equals x. Now we'll use our solution strategy for first order differential equations, but in this case, let's maybe do it a little bit nicer. And we can see that if we multiply by a further 1 over x squared, we'll be left with 1 over x squared y prime minus 2 over x cubed y equals 1 over x. So again, you could solve this just using the formula for first order differential equations, but since we've already done that, let's use this method. But now let's notice that the left-hand side of this equation is simply the derivative with respect to x of 1 over x squared times y. That's what we get using the product rule. And then that's going to be equal to 1 by x. But now we can take the antiderivative of both sides of this, And we'll have 1 over x squared y equals the natural log of x. I won't put a constant here because our goal is to find a second solution, not the most general one. But now multiplying through by x squared, we have y equals x squared times natural log of x. So that would be our second solution. And that's all that the problem asked for. But let's say if we wanted to find a general solution, of course, by the principle of superposition, that's going to be the sum of these two, or an arbitrary linear combination of these two. So perhaps it would be c1x squared plus c2 times x squared times log x. Okay, so there you have it. That was a full solutions for this exam. So maybe post in the comments how you would have done if this were your exam. And that's a good place to stop.